So, how's it going, everyone? My name is Francisco Mercado. I am a PhD student at UC Irvine. This summer, for the past few weeks, I've been working with Robin Sanderson on looking at some of the rotation curve tracers in simulated galaxies. Just to sort of motivate what we're working on, I'm going to show you all rotation curve and how we used to do it before Gaia. Really, if you assume some sort of potential or some mass in the galaxy, you can come up with a circular velocity as you go outward in radius. In the past, we've used several different tracers to sort of estimate what this should be for the Milky Way, in particular high mass um, disk stars, the terminal gas velocities or gas terminal velocities, red clump giant stars. Also, we could do James modeling of blue horizontal branch stars, and finally using some stream models. Right, we use all of these different tracers to sort of try to figure out the same thing. The big question really for this project is which of these tracers most closely follows this sort of true rotation curve of the Milky Way? Which tracer should we be using when doing this? And to answer this question, I'm using the FIRE2 simulations. So these are zoomed in cosmological simulations performed with FIRE2 feedback physics. We have 13 simulated galaxies in our sample that we look at. 7 of them are from these isolated sort of Milky Way-like halos in the latte simulations, and then the other 6 of them are from the Elvis simulations, which are sort of simulated local group or local volumes that contain the Milky Way and Andromeda analogs in all of these. And so I look at all of these individually. Just to give you all some background on the FIRE simulation. So here is a bunch of movies of all of the different galaxies. Some of them are not in our sample, but most of them that are in our sample are here. On the left, you've got the gas. On the right, you've got all of the stars. What FIRE does is it reproduces the different gas phases in the galaxy. It also tracks the metallicity as well as 11 chemical species, both in the gas and in the star particles. The stars that form in these galaxies, they form in dense self-gravitating molecular gas clouds. They have number densities greater than 1,000 atoms per centimeter cube. And finally, feedback from the stars is imparted into the environment from supernovae, stellar radiation, and stellar winds. So as you can see, all of these sort of have different histories. You saw all the, sort of satellites crashing in, and eventually you form these really nice disk galaxies that we see now that we're looking at here, right? Right, perfect. So just to show you all what we're sort of working with, I'm plotting just the half mass radius as a function of the stellar mass for all of the stars within 100 kpc. And so we just chose 100 kpc just so it encompasses the galaxy for pretty much all of these runs. And so we have, a range of masses between, roughly 10 to the 10.4 up to 10 to the 11 in stellar masses. And again, a good range of half mass radii. We do have a weirdo up here that should be M12R, and I'll talk a little bit about this as I go through it. But yeah, let's talk about the rotation curves in these simulations. So for one of the galaxies in our sample, this is M12I, which I'll be using as an example throughout the talk while I'm showing these curves. In the black, you see the actual root GM over R rotation curve for all of the mass within the sample, or excuse me, within the galaxy. And in the pink or in the magenta, we're showing the V phi of the gas. So this is the azimuthal velocity component if you grab the particles in cylindrical coordinates. And the cyan line is showing the same thing for the stars. And this is just grabbing all of that gas and all of the stars within 100 kiloparsecs. And you see that right off the bat, the gas seems to follow this black line, and it tracks it a lot better than the stars do. The stars seem to be having lower velocities out to large radii, and the gas kind of tracks this a little bit more. So as I mentioned, the question is, can we sort of make some cuts in density, in temperature for the gas, and then maybe age, metallicity, and maybe position for these stars, and get these lines to really track that black line as good as possible, right? So I do this first for the stellar component, and then I'll go ahead and move on and talk a little bit about what we've seen in the gas as well. But the first thing that I looked at was how stars in different age bands follow this. So what you're looking at is the same thing from the last figure, except now I'm separating the stars into these sort of age bands of 2 gigayears. And what we're seeing, actually, let me back up. I'm also now taking all of the stars within, you know, 0.5 above and below the midplane. And so what we're seeing is that for the younger stars in this galaxy, those tend to follow the rotation curve, this GM over R curve, the best. And so that's what we're seeing for that. But in particular, the youngest stars tend to trace this circular velocity the best. And so these are all within, you know, with the smallest age band being all of the stars within 100 megayears, which is what I'm going to sort of go into a little bit more. But this is sort of the first result that we've seen. Now, to show this for all of the galaxies, what I've done is you're looking at the difference between the curve of the stars and the actual GM over R rotation curve. So this is for all of the galaxies in our sample. If the line follows 0, then it perfectly tracks that rotation curve. And you see that for most of these galaxies, they do pretty well. Now I'm normalizing to the half mass radius that you all saw in stars before this. And so out to even a few half mass radii, this does seem to behave well or work well, at least within 25%. So it tracks that rotation curve very well. It's a large radii. Here's this weirdo again that I pointed out earlier. Some of these it doesn't work. I'll go into potentially why that is later in this talk. But essentially what we're seeing is that the youngest stars in the disk of a galaxy are born in the most circular orbits, and so they generally follow this GM over R rotation curve within 25% to large radii. So that's the first thing we see. The next thing I looked at was how this looks if you look in different directions in the galaxy. So if you have the disk galaxy, I like to call these sort of like pizza slices. If I look in all of the different directions, here I just do 8 azimuthal bins, and this works actually decently well. Again, now this black dotted line is just the full annular bin rather than just looking in different directions just to see what that looks like. And again, if all of this followed 0, then they track the actual GM over R rotation curve. And so again, this seems to work really well, you know, even better than 25%, which is what we saw in the past or in the last slide. Now to sort of quantify, I guess, what the scatter looks like, I'm plotting the V5 of the stars at the half mass radius as a function of the half mass radius. And I've shaded the region between the max velocity that we're measuring in all of the radial bins, and the error bars here are how much this changes, or this value changes as you look in different directions. So some of these have larger scatter when you look in azimuth, some of them have smaller, and in general, the scatter galaxy to galaxy is larger than the scatter when you look in different directions. And so that's sort of how I'm showing that here. Now, one interesting thing is that if you take that value of V phi at the half mass radius and plot that as a function of the stellar mass, you do get this really good relationship, a pretty tight relationship. And it's interesting because this is the weirdo that had a really low mass, and it still fits pretty well with that. The red line is just a linear fit to this data. And so what we see is that galaxies that have a more massive stellar component will tend to have a larger circular velocity. at least at the half mass radius. We also looked at the cut in metallicity. So here's the same thing we've looked at in the past, except now I'm taking the stars with the highest metallicity, particularly above 0.45 dex. Right, this is stellar metallicity, and still taking that that cut in position. And so it doesn't work as well. And so we sort of did this just to see whether or not if we believe that the stars with the largest metallicities are in fact the youngest, and this doesn't necessarily work because if you just look at the age metallicity relation for all of the star particles in simulation, when you look at the metallicity at the highest bin, you still have a large range in age, and so that's why we believe it's not really working as well. And this is the same for if you look at the alpha elements. So if you do magnesium to iron, it's similar. It doesn't work as well. So that's what we've found for the stars. The next, I'll talk a little bit about the gaseous component. So we made a couple of different cuts in temperature and density, particularly to sort of get analogs for a sort of cold phase molecular gas, neutral, and then finally warm or ionized. And we tried to see how well these different cuts in gas track that GM over R curve. So that's what we're looking at here. In the cyan, we have the cold gas. The blue, we've got the molecular. Orange, neutral. And then finally, the red, we've got the warm gas. As expected, this sort of gas, as we saw earlier, before making any cuts, that gas sort of tracks that curve really well. Now it's doing an even better job. Though it does seem to be kind of choppy at some of these areas. That could be either numerical for specifically the cuts that have very few stars. If you saw the cold cut, is way at the bottom of that temperature density space. And so that can come from that. Also potentially substructure, which I still have not looked at, but I do want to look a little bit more into that. So this is our residual plot that we saw now for the gas. This is the cold gas in particular. Again, for all of these galaxies, it's super choppy all the way out. And even with that, it still matches up pretty well within at least 25%. You've got a couple of the weird ones still showing up here. And now for the molecular cut, this is the cut with more particles in it compared to the cold gas cut. And so we see that this choppiness sort of still stays, and so that's what sort of leads me to believe that it might be substructure. Again, this is something that I still have not looked at, but it'd be interesting to see what that looks like. Again, still within 25%, it's following out to pretty large radii. This is, again, normalized to the half mass radius of the stars within 100 kpc. And so we've got also the neutral gas and the warm gas, which don't work as well as that, as the cold gas and the molecular gas cuts that we've made. And so again, similarly to the young stars, the coldest gas and the densest gas will track this GM over R curve well, at least within 25% out to pretty large radii. One thing to point out and to keep in mind is that this gas, the phi curves are a little bit less smooth than the curves in the stars. And so again, I'll be still looking into that moving forward, but it's definitely something to keep in mind. So the weird cases that showed up, if y'all saw the, it's particularly M12R and M12W that have their rotation curves or their V phi curves kind of fall off really quickly. I just kind of took a visual look at those just to see why potentially that was happening. And so we've got, at least for M12R, has this sort of half-baked disk, and it's still pretty thick. I should say that the red points are the stars, and sort of the greenish blue points are the neutral gas. We're doing face-on and an edge-on view. And so both of these have disks that sort of seem disrupted. I think M12R had recently gone through some merger, so we think that that might have affected how this circular velocity looks. And so I just want to show these compared to one of the other ones where this does work really well. Here we've got a really nice disk and a really thin edge-on look. And so at least visually you could sort of tell that, stars that don't have maybe settled disks or have some sort of interaction that has really disrupted the disk that could potentially not work well for these types of galaxies. Though moving forward, I do want to look at and see how we can sort of quantify this um, for how we can look at this in the future. Finally, I'll talk a little bit about just the future work. So some of the motivation behind this project comes from Kuhn et al. 2021, where they develop a Spitzer IRAC candidate. IRAC candidate young stellar objects. So these are all stars within a lot of these stars are younger than 1 mega year. And so could we use these stars to measure the rotation curve for the Milky Way? Another thing is that Eilers 2019 actually measure the Milky Way rotation curve with some luminous red giant stars. And so I'm going to use Ananke, which is something that Robin developed to have synthetic Gaia data from the fire simulations. And so I want to produce some comparison, for this paper using some of the red giants that are spawned from these star particles in fire. And I have run out of time, so I will leave you all with my conclusions and take questions. Yes.
Particularly interested in the discrepant cases. Can you give me an idea of how large the mergers were? And I can never remember the various names for the fire simulations. I thought M12I was also one of the cases that had experienced a merger, but maybe it wasn't very recent.
Right, it might not have been very recent. I think M12R was one of the cases that were, I think, supposed to be run with sort of LMC analogs. But that happened, I think, a little bit before Z of 0. And so I think that's what's going on, is that it sort of still has not settled after that interaction.
Mm-hmm. I see.
Can you talk a little bit about what the downfold, how this might be affected by the physics and be different from real life? You know what I mean? The difference between why you could be getting a different answer in the fire simulation. Than in real life.
I guess so. One of the things that the fire simulations are known for is really strong feedback, right? Haven't thought completely through how that could affect at least these rotation curves. It could make things, I guess, more turbulent environments, potentially maybe bringing down that velocity that we're measuring. But that's, I think, the biggest thing that at least fire is known for having pretty strong feedback.
Have you thought about any way to utilize the fact that you kind of have two independent tracers here to bring that 25% down, and how you would do that, and maybe use where you could have observations of both gas and stellar components?
So combining the different
components.
That's interesting.
They have similar, you're saying you have similar bounds that result. So if you could take the two, how can we work with that?
That's an interesting idea. I've not thought too much about that, but we should definitely chat about it.
We should hang out.
Since the microphone's already on, can you place some constraints on how likely we in the Milky Way are to be one of these weird cases where it doesn't work super well, since we are in the process of merging with both Sagittarius and the Magellanic Clouds?
Yeah, that's interesting to think about. I have not done much work on trying to place those constraints, though. That's one of the things I do want to look at. And one of the questions that we do want to answer is how do we even know if we're in M12R or M12W, right? So that's one thing I want to look forward to doing. I think talking about just the LMC, right, and its effect, I think the LMC is still, we believe, on first infall. So maybe the LMC has not, come through the disk and disrupted that, but Sag has, and so be interesting to think about that a little bit more.
Hi, Francisco. Very nice talk. I had a question about. Actually, I had two questions. So the first one is about the fact that you saw that the young stars tend to track the circular velocity curve the best. So is that because the old stars, they are born in radial orbits mostly, or do their orbits become radial over time? Or
that's a good question. I've not thought too much about why the older stars don't form, don't follow. It could potentially have to do with maybe where, how they formed, as you mentioned in the past. It might have something to do with the fact that they were born before the disk had settled to the point it is now.
Okay.
So that's sort of, I guess, naively what I would think.
Okay.
But yeah, I definitely want to think a little more about that.
So my second question was about basically the plot that you showed for the velocity as a function of radius. For the gas, I found, or maybe for the stars as well, I found that towards the outskirts, the slope is different from square root gm over r. Even if the gas was like following the curve very well for a long time, but then eventually the slope becomes less than. So do you have any idea like why that is happening?
No, I'm not too sure exactly why that is happening. I guess in the outskirts we do have, more of the gas that is not sort of following the disk. We're talking more about that gaseous halo. But yeah, no, don't have too much.
Okay. Thanks.
Question, but I don't think let me see. I can't resist commenting on this last exchange about the young versus old stars, because of course there is a classic question about why the older stars are on less circular orbits, right? So your answer, Francisco, is one of the answers, and it is thought that some of the thicker disk stars are formed in things like M12, whatever it was, the crazy one. Early on galaxies, they're known as chain galaxies, have some blobby star formation, and you can get stars forming in thick disks, which was not a classic model. The classic model is that stars form in thin disks, right? And they get heated, right? So there are two different, you mentioned one, I just had to mention the other one.
Thank you. Yeah, that is another.
Yeah.